Okay, so now we look at lecture 5. So in lecture 4, we end up at this band diagram. So this basically is two lines in a spatial coordinate system. So the two lines basically indicate the position of conduction band bottom and also top of a valence band. And in between, there's a gap. So this gap is basically called band gap. So at the low temperature or zero temperature, so all the energy states below this EV are completely filled up by electrons. And above the conduction band edge, and so other states are empty. So in this case, since when you apply electric field, and so electron cannot move in the valence bands because complete fill up, there's no empty state. So that's the reason why there's no electrical conduction. So this means, in other words, semiconductor at a very low temperature, so basically is an insulator. Excuse me. So in order to make a semiconductor conductive, and we need to find ways to introduce free carriers. The most common way to produce free carrier is by thermal excitation. Anyway, this is happening all the time at a finite temperature. So this means that some of the electrons will be excited to the conduction band, right? And then this will generate the free carriers. But this process is not very efficient. So that's the reason why we need to find another way, which is called doping. And this will be very important, all right? And so we'll talk about the details later. But anyway, so eventually you have two types of semiconductors. So one is called intrinsic, and the other one is called extrinsic. So after we finish this part today, and then next week, the next lecture, we'll talk about electron transfer. This means how the holes can move in the semiconductor in order to carry electricity. Now, so lecture 5 has 3 parts. So in the first part, we'll talk about the thermal equilibrium carrier concentration and then Fermi level of intrinsic semiconductors. And after that, we talk about doping and also carrier concentration in extrinsic semiconductor. Okay, so I actually already explained this part in the introduction. So basically, for normal semiconductor, for example, we just use a silicon as an example. So you can see that once all the silicon atoms come together to form a crystal, and so each silicon will contribute and 4 valence electrons. So those 4 valence electrons, for example, look at this one, 1, 2, 3, 4. And then, so these 4 valence electrons will interact with valence electrons of neighboring, nearest neighboring atoms. So we have 4 as well, 1, 2, 3, 4. And then they form a very strong covalent bond. So in this case, so basically you can see that the 2 neighboring silicon atoms share the electrons, right? So the electron cloud or wave function from the 2 atoms but overlap with each other and form a bonding state. And this state will determine the strength of this state, will determine the band gap, right? This is the one we talked about in last lecture. So when this band gap is large, and then at the low temperature, of course, if it's at absolute 0 temperature, and so even this band gap is small, and then you will not have any free carrier or electrons in the conduction band. So all the electrons are basically in the valence band. So the valence band is completely filled up, so you don't have any empty states at the valence band. So therefore, when you apply an electric field, so electric field, you know, is a driving force for any charged particle, right? So when you apply electric field, and then so electrons in the valence band are unable to move, because if for electrons to move, you must have vacancies, and so that the neighboring electrons can just move to the vacancy, and after that it creates another vacancy, and then for the other electron to fill up. So by doing so, the electron will start to flow. But when this band gap is finite, and it's at zero temperature, and then this is not possible. And however, at the finite temperature, so it means that when T is greater than 0, there's always a probability, no matter how large this EG is, statistically, there's always a probability, finite probability for electrons in the valence band to jump to the conduction band due to thermal excitation. When this happens, when you apply electric field to this semiconductor, and then of course, electrons will move against electric field direction. That's because you have an empty state here. At the same time, you have holes here. The holes will move along the electric field direction, right? And because you have an empty state here, and then eventually, you have the electric conduction from both the hole and the electron. So remember, electron and the hole are the charge, excuse me. So electron is a negative charge and hole is positive charge. So therefore, although electron and the hole are moving in the opposite direction, the current is still in the same direction. So that's the reason why both will contribute to electric conduction in additive way, right? Okay, now in order to, when you say for example, when you apply a certain amount of electric field or driving force to this semiconductor, and then so in order to calculate how much current which can be carried by this semiconductor, then we needed to know first the carrier concentration first, right? So this means that per unit volume and how many electrons or how many holes do you have? And then of course, once we know this, and then in next lecture, we'll talk about how fast this charge can move. So these two factors combined will determine the current density, right? So now we just look at the carrier concentration first. So we try to calculate the number of electrons per unit volume at a finite temperature in the conduction band, all right? So though this, when you look at this, the basics again, as I just explained, at the zero temperature, so the number of electrons per unit volume and per unit energy interval in the valence band, all right? The valence band is basically is given by this density of states. Okay, so at zero temperature, and of course, so the number of electrons you have per unit volume within a small energy interval, for example, is shown here. Well, maybe I just explain this four diagram first, and maybe it's easy for you to understand. So basically, what's shown here, this is just the band diagram. So we have a valence band edge and the conduction band edge, and then this is a band gap. All right. So our energy is in this vertical axis, is energy. Okay. As we explained in the previous lecture, you can put your energy reference, say for example here. So if you use this EV as a reference for your energy, and then so this will be 0, and then this will be EG, all right? And of course, you can put your reference here. That's your choice, right? But once you choose a reference for the energy, and then you have to indicate other energy level accordingly. Okay, so and at a finite temperature, and then some of these electrons will be excited to the conduction band. So that's the reason why now you can see that you have, say for example, in this case, you have 2 electrons and then 2 holes here, all right? And of course, statistically, you cannot just try to count this. You have to use statistical method to capture this, all right? So to do this, is not very difficult at all. And so first, we need to know what's the density of states. So this means that at each energy level here, and so what's the density of states? So remember, and each K state can accommodate 2 electrons, but each energy level can accommodate more than that. That's because that many electrons with different K states will have a similar energy. So that basically is a density of states, which we explained before, all right? So that basically this one. So it's a density of states. So again, this is the energy, and then this is density of states. And then density of states is 0 between in the gap region, because in the gap region, there's no states, empty. That's all. That's why we call this a forbidden gap, right? And then when you move away from this band gap region, so in the conduction band, you can see you have this density for electron, which will increase parabolically respect to energy. And similarly for holes, and you can see density states will increase in this opposite direction when energy increases in this direction. All right. So now at the zero temperature, and even you have density of states here for in the conduction band, but you don't have any electrons in the conduction band because at the zero temperature, electron cannot jump from a valence band to conduction band. And however, at a finite temperature, and then you know that we have this Fermi-Dirac distribution. So this means that above the Fermi level, so this is the Fermi level for intrinsic semiconductor. We'll talk about this one later, but anyway, we should be able to find out so where the Fermi level is. But now I just draw it here, which is roughly at the middle of the band gap. All right. So now, and so above the Fermi level, and then we have a finite distribution of this electron probability. And then, of course, below Fermi level is not completely unity or one because this is the finite temperature, right? So, and then, so this means that, so once you have the states, and then this state is occupied by the tensor state, right? It's occupied by a certain probability. So that's why, so the number of electrons you have within that unit and interval is simply the product of this one to this one, right? Although looks like that this probability is almost approaching zero. However, since this tensor state will increase with energy, that's why the product of this one will have this kind of distribution. So you can see here, all right? So below this EC, because this is a forbidden gap. So that's why, because density of state is basically zero. So that's the reason why even you have a finite distribution probability, the product of this one and this one basically is zero, right? However, above this EC, so you have this finite distribution, right? So initially it's zero, and then it will increase with energy, and then you reach the maximum. And after that, when energy increases further, so this will gradually approach zero, right? So the total number of electrons you have in the conduction band basically is just to integrate this product respect to energy, right? So this is the DE, basically this is small energy interval, right? So this small energy interval multiplied by this is an electron, number of electrons you have within this region. And then for the entire conduction band, and just to integrate respect to E from EC, that's here, to infinity, right? It's infinity. So after integration, so what do you get? Remember, this F basically dimensionless, right? There's no dimension for this, it's just a distribution probability. And then this density of states is the number of electrons per unit volume in real space and then per energy interval in energy space. So that per energy interval after multiplied by this energy, so this means this energy dimensions cancel out. So eventually you only have a dimension for the whole integration is number over volume, right? It's the number of electrons per unit volume. So what's that? That basically is electron density, right? Electron density basically is number of electrons per unit volume in real space, right? So it means after this integration, then you should get a physical quantity with a dimension of 1 over volume. That basically is a concentration, okay? So all this I actually explain here. So it means that at the T is not equal to 0 when T is finite, and then the number of electrons per unit volume. So I always use per unit volume here. That's because it comes from here, all right? And then within DE is given by this one. And then total number of electrons per unit volume. So after you integrate with the energy, and then you don't have energy anymore, and then so that basically is a electron density. Okay, so I hope this is clear, all right? Now, we need to look at so how to calculate this. So I mean, how to calculate this integral. So this is the integral I just rewrite here from the previous slide. So first, so you have so this product is called integrand, right? So this is the integration variable. So the range for integration are given. So this is a definite integral respect to a single variable, right? You learn this in mathematics. So now we just need to find out the closed form of this density of states, and then this form distribution function, right? So density of states. So if now we are unconcerned about a single band and a single valley, so that basically is given here. So this is what we already derived in last lecture, and this is very similar to the density of states of free electron in 3D case, right? So what we did that we just replace this M by effective mass. This is for, by the way, for a single band and single valley, okay? And then this E, so for single electron, the reference is from 0. And then for a semiconductor conduction band, the reference is from a conduction band edge. That's why I have E minus EC. So this means that at the conduction band edge, so this E should be EC minus EC is 0. So that's why it's similar to this one, right? And so, and then we just substitute in here. So this is basically the function of E only, because EC is a constant. And of course, the electron Fermi distribution function for electron is given by this one. So again here, so all these are constant, and T is temperature, and then we only have E, which is a variable, and then EF basically is a constant for a certain type of semiconductor. This one later we'll talk about this. Okay. So and then we substitute this one and this one in here. Usually you were to integrate this and to find out the electron density. And similarly for hole, so density of states for a single band, valence single valence band, and then for hole, so basically it's given by this one, right? So just noted that, so here, because E is increasing in positive direction, and then this E is increasing in negative direction, so that's the reason why we have this EV minus E, okay? So EV is larger than E. So so when you write in this, so basically we use the same energy direction that basically is pointing up. So that's why when EV minus E, so the E basically from if EV is a reference, and then this E will be from a minus infinity, right? So that's how we define this energy for electron the whole. And then you substitute in here, and then you can integrate, make a kind of P, right? So here, so all the parameters defined here, right? So so I don't need to repeat this one again. Now, so we just try to calculate this N and P using this integral. So before we do this, and then we notice that for most of the semiconductor materials, right? And actually you also notice, from here. So for example, you notice here, so this this distribution actually is far away from this EF or just the band gap, right? So that's the reason why. So this distribution here actually is, although it's a Fermi-Dirac distribution, but it's approximately the same as a Boltzmann distribution. This is what we talk about when we explain the Fermi distribution. And if you forgot about this, you go back to check that again, or just look at this scale of these two variable window, right? And because so this is still Fermi-Dirac distribution, right? So E minus EF is half of the band gap. So if the band gap is much larger than the thermal energy of this KBT, remember KBT at the room temperature is 25.6, 0.9 millielectron watt, right? So if the band gap, say for example, is 1 EV, and then so 1 EV is 1,000 millielectron watt. So 1,000 divided by this 25, you get about say 40, right? So e to the power of 40, you can see that this is going to be a very large number, and then so that's why I just simply ignore this 1. Ignore this 1, and then so this will be flipped over. So now by right, you should have a natural sign here if you use E minus EF. Since I use EF minus E, which is different from this one, that's why there's no negative sign here. And then so this is this integral, and actually you can try to compare this one with some of the integrals in mathematical handbook, right? And then from there you can integrate and just use some approximation. So we'll not do this because this is considered as a mathematical problem. And then people have done it. So eventually, after the integration with respect to E, and then you obtain this very nice interesting form. So basically, the carrier density is given by a prefactor, right? Which you can see that it's a function of temperature only, because mass, if the semiconductor is fixed, and then electron mass, effective mass is fixed, and h is Planck constant, and Kb is Boltzmann constant. So that's why it's only dependent on temperature, right? And then multiply another very important term density, which has an exponential form, right? So you can see this exponential minus EC minus EF divided by KBT. So obviously, you can see that when EC minus EF is positive, and then this whole thing will be a small number, right? So it means that when EF is below EC or far away from EC, and this will be a very small number, and eventually multiply this one, you get a very low carrier concentration, right? And when EC is equal to EF, this means when EF is approaching EC, and then this will be 0. So it means the whole thing, this term will be 1, exponential factor will be 1. So when this is 1, and then this n is equal to NC. So it means the NC is a very interesting number, right? So, and of course, when EC is, when EF is larger than EC, and then this number will be a very large number. So this means this n can be larger than NC, right? So it means NC is some sort of measure of carrier concentration when EC is equal to EF. So this actually is the name of this. This is called effective density of states in a conduction band. Okay, so you still remember density of states, right? So density of states is a number of electrons or holes. Say for example, just focus on electron first. Number of electrons per unit of volume in real space, and then per energy interval in energy space. But this NC is different. So since you have already done the integration for E, for energy E, so that's why it basically is the number of electrons per unit of volume, in the conduction band, right? But why? Because it's effective, because the electron concentration in the conduction band is not just on this one, also given on where the Fermi level is, right? So that's why when the Fermi level is at the EC position, and then so this NC basically is the electron concentration. So if not, and then you have to multiply this NC by either a number smaller than 1 or less than 1, and to get the real carrier concentration. So that's why this is called effective density of states in the conduction band, right? It's not a real carrier concentration. Okay, and you can do the same thing for hole, and for hole you have to integrate from -infinity to EV, and then again just use a Boltzmann approximation to replace this Fermi-Dirac distribution, and then you get a integral which is very similar to this one. And after integrate, again you get the same form for the whole concentration. Now this prefactor. So now for electron, this is an electron effective mass. So for hole, this is a hole effective mass. That's the only difference, right? And then again, so we just call this as MV. So this MV is called effective density of states in a valence band. So what is number? So that means that when EF is approaching EV, and then so your whole concentration of this is equal to this one, right? So when EF is above EV, and then this whole thing will be smaller than 1. This means the carrier concentration is smaller than this. So when EF is below EV, and the whole thing will be larger than 1, and then this will be whole concentration will be larger than this, right? So this means that you can see at a fixed temperature, and then AC and MV are fixed. So if you can find a way to adjust this Fermi level, and then you should be able to control the carrier concentration. That's the basic essence of these two equations. Okay. Now, we try to calculate this NC, see what's the scale of this NC, right? Because roughly from NC, we will know, once we know the Fermi level, and we should be able to know the carrier concentration in electron concentration in the conduction band, right? We're talking about NC. Okay, to do this, we just look at a simple case first. We assume that this electron effective mass is dependent on the semiconductor, right? So different semiconductor, we have different electron effective mass. But so roughly, is maybe a little bit less than the free electron mass, but anyway, will not be too far away from a free electron mass. That's why we just assume that this is equal to free electron mass, and also assume that temperature is room temperature. Okay, and then we just substitute in. So H is a Planck constant, and then we can calculate this and see. When we do all the calculations in this module, I hope you understand one thing. And so all this Boltzmann constant and also Planck constant and then effective mass, they do have a dimension. But if you use this international system, and then you find that it's very difficult to convert all of this from one to the other. So normally what we do that, just try to look at the internet. You search for the internet. So all this fundamental physical constant can be written in different units, right? So that it's easy for you to convert it. For example, mass of electron, free mass of free electron can be written like this. And you know that by right, the dimension for mass should be kilogram or gram, right? So that's basically according to the international unit system units, and then you write this. But we don't need to follow that, right? Because we can always put this as a EV divided by C squared. You check from internet. This is we do have this kind of expression. Of course, if you want to calculate this one, and so V basically is watt, the unit for voltage, right? E is electron charge, and C is speed of light. You give here, and you put in, you should be able to find out electron mass in kilogram or in gram, right? So you should be able to get exactly the same number as listed in the textbooks. And in the Planck constant, so the Planck constant can be, of course, you can use joule and a second, right? So sorry, this should be small s, joule and a second. And then this will be the number, right? And so of course, you can also use, for example, EV and then second. That's what you can do. That's your choice, right? Because joule is a dimension of energy, and the electron volt is also dimension of energy, right? And then we just substitute in here, and then so Boltzmann constant. All right, so this is the let me see. So the Boltzmann constant, you can see kBt. Okay, sorry, so this k should be small k because I know this kB. Okay, so we don't use kB Boltzmann constant and the temperature calculator was kBt. So what we do that we just, because we know that the kBt at room temperature is given by this one, and then we just need to the other temperature, we just scale to other temperature, right? That's very easy. So now since it's room temperature, then we don't need to do anything, don't need to scale. So we just substitute in 25.9. So this basically in this one, right? 25.9 times 10 to the power minus 3, because this is the milli, right? So that's what we have. And then so this is the electron mass, right? 0.512 times this one. So the dimension put here. So EV is the dimension for kBt, and then for the mass we use EV over c squared. So this one, and then divided by the Boltzmann constant, right? So this is 2 pi and the Boltzmann constant. So the dimension we use is EV second. So that's this one, right? So now you just calculate this number. It's very easy. You can do it by yourself. And then dimension-wise, so now you can see that you have EV here and then EV here, and here is EV squared, right? So EV squared, EV, so this cancels out. So now you have this speed, right? Speed. So C to put here, so C squared put down, so C dot S squared, and this one, okay? So this one just put here. Now this is C dot second. So when you have C dot second, so the second is gone, right? Then you have a meter. So that's why, so this here you get a meter square. So the meter square, so basically as here, right? At the denominator, right? And then take the square root. So you get a meter. So basically, so meter you flip over, it becomes negative, and then there's a cube here. So you get meter to the power of 3. So this basically is concentration, right? So that's a dimension of this one. And all other units are gone. Okay? And then you just have pure numbers. You calculate this one, and then you can find out that it's given by this. Okay. So now you look at dimension of this, and see it's a concentration. It's something like a number per unit volume, right? So as I explained that when your EF Fermi level is approaching EC, and then the electron density should be equal to this one. And then, so now we should be able to compare this one with the electron density in a typical metal. We then put in copper. So we used this before. And so the carrier concentration basically by this. Okay. So now this is just about 2 orders larger than this one. So it means that, so this is 100 times of this one. Okay. So now if your semiconductor eventually has a concentration which is compared to this one, and that is not useful because you cannot control it anymore. And if that's the case, why not just use the metal, right? Because metal is more conductive. Why we don't use metal for electronic devices? Because this concentration too high, we cannot control it. So semiconductor is good because this anyway, this is 100 times more than this one. And then if you want a even smaller carrier concentration, and then you just to make sure that this term is smaller than 1, right? And then you get carrier concentration is less than 1% of that of copper, right? If you want something which is comparable to metal, and then just make this one larger than 1, right? And then you have a higher carrier concentration. Of course, in that case, most of the time you don't use it as a semiconductor anymore. You just use it as a, something like metal, like a conductor, right? So that's the reason why this is a semiconductor is very important. And you also here, you know that this EF is an extremely important parameter. So for semiconductor statistics, so the only single parameter which is important is the Fermi level. If you can control this, and then you can control the carrier concentration in the semiconductor, right? Of course, in metal, you cannot do that. In metal, this EF is always fixed. So later I'll talk about this one. Okay, so now for real semiconductor, you know that you have not just a single band, right? Conduction band is single, but the conduction band is a multi-valley, right? So and then valence band is a multi-bands, single valley but a multi-bands. So that's why, and for single band, single valley, so your NC and V is given by this one. But for semiconductor with a multiple valley, and also anisotropic effective mass means the mass is not the same in all different directions. And then the effective density of states are given by this one and this one. So NC, you can see what's the difference. So since you have multiple value, that's why you have put here, right? And since your mass is anisotropic, that's why you use this density of states effective mass, which we derived last week. Okay, in last lecture, is a density of state effective mass. So that basically is given by this one because the mass is different in x, y, z direction. But in general, if you rotate according to x, as we explained in last lecture, so the last two can be the same, but the first one different. But anyway, so this is how you can calculate this density of state effective mass for electron. And then for hole, you typically you only have a single value, right? So for silicon, for example, this MC is 6 here, and for hole young, so you only need to find out what's this, but it's a multiple bands. So that's why you have light hole and heavy hole. So the effective density of effective mass, this one is given by this. This is already derived in the previous lecture, right? So that's the only thing you need to know. And after that, just substitute here, and then substitute this one in here, and substitute this one here for a specific semiconductor. And then you should be able to use the same equation to calculate the carrier concentration. Okay, so now we look at the intrinsic case. So remember, intrinsic semiconductor means that at the zero temperature, you don't have any free electrons here, right? So all the electrons here. And then at the finite temperature, so some of these electrons will be excited thermally to the conduction band. So now you have electron here, and then you have a hole here. So the number of holes here and the number of electrons here are exactly the same for intrinsic semiconductor, because when one electron jumps from here to here, you get one electron, and then you create a hole, one hole at the same time. So if you have two electrons jump from here, you create two electrons here at the same time, you create two holes here. So that's why they're always the same. So N and P is equal. Okay. So and then so this is the N, right? So we just calculated. So remember now we use MC here, and also we use this density of effective mass here. And then this is for hole, and then MC is 1, so MV is 1, so single value, but multiple bands, right? That's why this one. So now we can see, of course, temperature can be canceled out. So just rearrange this equation a little bit, and then we can find out this EF. Right? As I just said, EF is the single most important parameter for semiconductor statistics. So this means once you know EF, and you know many things about this semiconductor, right? So, and so this EF is simply given by two terms. So the first term is EC plus EV divided by 2. So what's EC plus EV divided by 2? Of course, your EV, the energy reference can be anywhere, right? But suppose your energy reference is here, and then so EC is EG, and the UV will 0. So this means EC plus EV basically is EG, is this band gap, and divided by 2, so that basically this one here, right? At the middle of the band gap. So of course your reference can be anywhere here, and then EV, and then plus the EC divided by 2, you still get this middle of the band gap, right? So now, and then you still have this term, but this term actually is very small. Okay, so this term eventually, this term, anyway, KBT is only 25.9 milli electron watt, which is much smaller than that of EG over 2, right? And then these two are roughly the same. These two are roughly the same. So when these are roughly the same, so log of 1 is 0, a very small number. So this very small number multiplied by this very small number. So eventually you get something here which is negligible small compared to this term. So that's why eventually we can say that for intrinsic semiconductor, the Fermi level is always near the middle of the band gap. So in the first approximation, you can always assume that for intrinsic semiconductor, the Fermi level is the middle of the band gap. Okay, so that's a very important finding. So now, once you know this Fermi level, right, for intrinsic semiconductor, you know the Fermi level as the band gap, then we should be able to find out the carrier concentration, right? So since N and P is the same, we'll try to find out the NP product first. So the NP, so again, we substitute N here and P here, right? Then try to find the product. So you look at this product now, this product does not contain EF anymore, right? There's no EF. So why? So EF can be removed anyway, because in intrinsic case, EF is always the middle band gap, right? So that's why, in principle, you can use that EF to calculate the carrier concentration. That's why we do it. So here we use a different way to do it. So basically, we just find out what's the NP product. Since N equals P, and then so we know that the NP equals Ni squared, right? So by the way, so this NP product, so this is called law of mass action in semiconductor, right? So why this is the case? It's just like a chemical reaction. So law of mass action actually talks about the rate of chemical reaction is proportional to the product of concentration of reactants, right? So here, when we use a thermal process to generate a hole in the electron, it's something like chemical reaction, right, to generate a free carrier. That's why we just simply call it a law of mass action. There's no specific meaning anyway. We just, since it's similar to chemical reactions, we just use it. Okay? So, and in this case, this NP is equal to Ni squared. Okay? So, by the way, and this actually is true for even for extrinsic semiconductor, which we'll talk about later, right? But anyway, for intrinsic case, since N is equal to P, we just call it Ni, both Ni. So that's why NP will be Ni squared. So this basically, this will be Ni squared, and then we take the square root of this one, and then we can find the carrier concentration for intrinsic semiconductor, which is a function of temperature and then band gap, right? So here's the temperature here. So Kb is the Boltzmann constant, and then H is the Planck constant. And then of course, when the semiconductor is chosen, and then it's the MdE, MdH, and MC are all constants. So that's why eventually this intrinsic carrier concentration is just a function of temperature. Because if your semiconductor is given, and then Eg is also given, right? So if we look at a simple case, we just let this effective mass be the same as a rest mass of a free electron. Just simplify this, and then can find out this intrinsic carrier concentration as a function of temperature and the band gap. Okay, and then here we just show some value here. For example, when Eg is 0.1, and then so what you got is this one. All right, remember this number, and is much smaller than that of NC, because NC, remember, is 26, right? NC. So then the electron concentration, even at this small band gap, is smaller. And then we increase the band gaps, for example, to 1. This is typically, quite close to silicon. And then you get this 10 to the power 17, which is a very small number, right? So remember, for copper, this will be 28. This is 11 order difference. However, you can control this by changing the temperature. Okay, so we increase the temperature to a high value, and of course this will increase. So now, because we use room temperature, so this is what we have, right? Now, just talk a little bit about this EF, since this EF is so important, right? And then what exactly is the Fermi energy? So if you in semiconductor, we already calculated this Fermi level using the free electron model, right? So we know that at zero temperature, and then below Fermi level, and then so all the energy states are completely filled up by electrons, and then above this is zero, right? And at a finite temperature, and then you have this kind of distribution. Okay, so this EF, why EF is here? Remember, EF is determined by the carrier concentration. So if you forgot about this, you go back to check a previous lecture again. So when carrier concentration increases, and then EF will increase. Why this is the case? Because you always fill up this energy states from the lowest energy first, right? And then gradually move up. So when you use up all the electrons per unit volume, that basically is the carrier concentration, right? And then you stop here. That's your Fermi level. So imagine if you want to add another electron to this Fermi C, so that another electron cipher number is infinitely far away from this material. And then when you move that electron from infinitely far away to this material, and then you need to add energy of EF. Why? Because otherwise you cannot put the electron here, right? You cannot just put that additional energy here because that's already occupied. This, right? So that's the reason what's EF. So this EF exactly is a measure of total chemical potential, okay, or electrochemical potential of electrons in the body. So if you have a large number of electrons per unit volume, and then you have a high this so-called chemical potential. All right. So now, if you so this is chemical basically of a body is a thermodynamic quantity. So this basically is corresponding to the thermodynamic work which you need to do in order to add one electron to it. So this is what I already explained, right? So when you try to add an extra electron here, you cannot put here because these are already occupied. So that's why you must put it here. But the electron energy far away basically is your reference, right? 0. And then you want to put here, you must add this amount of energy to that electron, and then you can add here. Otherwise, you cannot do that, right? So at the finite temperature, so what this? So this basically, since it has followed this Fermi Dirac distribution, so this is just an energy level inside this material at which you have 50% of a probability to occupy this energy level. So this, if that's the case, this is basically the Fermi level, right? So there are two ways to understand this. So first way to understand this is at zero temperature, the Fermi level basically is the energy which you need to add in order to add one electron, to move one electron from infinite far away to this Fermi C. That's the energy you need to supply. Or the other way to understand this at the finite temperature is just an energy level at which the probability for electron to occupy this level is always 50%, right? So that's another way to understand this. So that's a Fermi level. And so for metal, it's very easy to understand, right? And what happened to semiconductor? And the semiconductor, just now we already found out that for intrinsic semiconductor, so this EF basically is the middle of the band gap. Okay, so now at zero temperature, and so we know that all the states below EV are completely filled up. And then, but for metal, we said that below EF are completely filled up, right? And then what happened in semiconductor? Why below EF here that's not filled up? That's because that the semiconductors are different because you have a forbidden band gap here. So although in principle, statistically, you can fill up the states, right? below the Fermi level at the zero temperature, but you don't have states here for you to fill up. So that's because density is 0. So that's the reason why you only fill up to here, okay, up to EV. So below this, completely fill up. And then below EF, so here there's a half of the band gap, which is a region where you don't have the states to fill up, right? You can fill up, but there's no state to fill up. So that's the reason why EF, is here. This is not difficult to understand. Just imagine that if you have a semiconductor with a 0 band gap, this means the EC is infinitely approaching EV, or band gap is infinitely small, and then eventually, of course, EC, EF, EV will be at the same level. That basically same as a metal, right? So that's what you see. So now, why is semiconductor so interesting? That's because that for metal, it's very difficult to change EF. Why? Because you have so many electrons here, just like water in the ocean, right? You add 1 drop of water in the ocean, the surface of the ocean will never change, right? The water level will never change. Now, in order to change the water level of the ocean, you need to add a huge amount of water. And similarly, if you want just to pump out 1 basket of water from the ocean, nothing will happen, right? So this means that the water, the surface of the ocean is mostly constant, right? Like this. But semiconductors is different. Semiconductor, because the number of carriers you have are very low, right, in semiconductor. So that's the reason why when you add a bit more electron to this, and what happens? This will move up, right? So why does it move up? So when you add electron to this one, when you add electron to this, so next, when you want to add more, and then you have to increase the energy, right? You need to supply more energy. So that's the reason why EF will move up, okay? And similarly, if you add holes here, what does this mean? This means that you remove electron away from here. When you remove electron away from here, of course, this EF will drop. Why? Because since you have removed it, so the next, when you add 1 more electron to the system, you don't need the extra energy to add to it, or the energy you need to add to it is very small. So that's the reason why. So this will move down. Okay, so this means that if you can find a way to move this EF up and down, within this region, so in principle, you can control not just carrier concentration, but also conductivity. Because when EF is above this middle of band gap, and then you have more electrons. So this means you have what we call N type. And then if EF is more towards the EV, and then you have more holes here, so we call P type. That's interesting about the semiconductor. So this means that you can not only change the carrier concentration, and then you can also change the type of carriers, dominantly N type or dominantly P type. This will allow you to design and then fabricate the transistors, right? Which is extremely important. Now, if you look at typical intrinsic carrier concentration in germanium, silicon, and gallium arsenide, so at room temperature, like given here, right? And then of course, when you change the temperature, you increase temperature, and then the carrier concentration will increase. So here we show 1/T, and typically in this module, later we'll also use this one. We don't use T because use T. Why we don't use T? Because if you look at this carrier concentration, and so what we derived, so you can see this exponential function is also 1/T. So that's why when you use 1/T and then use log scale, and then you can plot this one and as something proportional to 1/T. This means log P is proportional to 1/T, and then log N is also proportional to 1/T. But after you take a log, there's a negative sign here, right? So that's why the slope is always negative. So that's how we plot it. And also, we don't simply use 1/T because T typically room temperature. So 1/300 is a very small number. It's difficult to to handle. So that's why normally we just put the 1000/T. So that's why when T is 300, and then this is 3.3 somewhere here, it's easy for you to understand, right? So that's why we use this. And of course, if you use temperature, you can see that the scale is nonlinear, right? So if you use this 1/T, and there's a linear scale here, and then this will be log scale. right? And then you get the straight line. So this is slope is determined by the band gap, so or other constants. Okay, so but anyway, you can see that when temperature increases, so temperature will increase in this direction, right? In this direction. But when it's small, in temperature high, because it's 1/T, and they have higher concentration. Okay, so that's what you see. Okay, so we'll just stop here for a while, and then next we'll look at extrinsic semiconductors. Means how to make a semiconductor more conductive even around the room temperature.